Friends, here I am explaining something more about Snell's law. You know, sin I by sin R is equal to constant. Must watch my last lecture about that light, then come here to understand properly. So here, if rarer to denser the light will go, it will bend towards the normal. You can see actually it can go that way, straight line. This is straight line, this is straight line, but it will bend towards the normal. You already learned it. Now students, if the medium fixed, we know if the medium is fixed, sin I by sin R will be constant, means the sine of angle of incidence to the sine of angle of refraction is equal to constant, and this value you can say mu until medium remains same. So students, for example, I give here, suppose this is two medium, same medium. If light fall like this way, here the angle of incidence is I and R, angle of refraction. Similarly, you see in different angle light fall here. Suppose we call it I1, R1, and here I2, R2. Then you can see for two medium, sin I by sin R is equal to sin I1 by sin R1 is equal to sin R2, I2 by sin R2. That is I2 by R2 is equal to constant. Understand? Now I think you can easily understand the Snell's law. Means what will be the angle? What will be the angle? I1, R1. What will be the angle will be there, but its ratio will be fixed, constant. Okay. Now students, directly move 4.6. Okay, topic 4.6, you can see there, refraction of light through rectangular glass block. It is important, maybe come in the exam. You must draw what I am drawing one by one on it. You just draw it, that refraction of light through a rectangular glass block. Very easy, in 2 minutes you can draw it. Students, first you draw the glass block, rectangular. Now, if the light ray pass suppose we consider monochromatic, means one single wavelength light we are calculating, because different wavelength have different refraction. Okay, you know different wavelength has different amount of refraction, because you know the relation V is equal to F lambda. You remember this formula, means velocity is equal to frequency into frequency of that light into wavelength of that medium. Okay, that is the speed of light is equal to frequency into wavelength of that medium. These both will depend on the speed of light. So we will consider one single monochromatic light. See, when it will fall, suppose this will fall, you know there is the normal, this is the surface, so perpendicular, that is the normal. Okay, so suppose this is the I, angle of incidence, and this is R. You know when pass from air to glass, means rarer to denser, glass is denser, means move towards the normal. So towards the normal it will fall here, towards the normal. Okay, actually the light ray can go through like this way, but it will move towards the normal. This is the normal. Okay, after falling on the second slab, second portion, second refraction again happens. You know students, how? Students, after falling here, you know, from when glass to air to glass to again move to the air, here air is there. So you know from denser to the rarer means move away from the normal. So this is the normal. Okay, actually the light can go through this way, but it will away from the normal. And students, this is called emergent ray, and this angle is called E, angle of emergence. Okay, angle of emergence, because the light ray is coming out from this slab, it will looks like that. Okay, that's why it is called angle of emergence. Okay, or emergent ray. And students, it has seen that angle of incidence is equal to angle of emergence. Okay, experimentally it has seen that these both angle is same. So just nothing happens, the light ray fall here and it is going through this. Okay, go, light ray fall, again bend, again go. Only its direction changed. Student, light ray can go through this like this way, but only slip a little displacement takes place of light ray, otherwise everything same, because you can see what the angle of incidence, emergent angle also same. So just little bit displacement happens, actual from its actual line it will displaced, that is called lateral displacement, and it has seen that this both is parallel. Okay, that emergent ray and that incident ray, if you long it, then you can see this both is parallel. Okay, so that is called lateral displacement. Okay, means parallelly a displacement of light takes place from this portion to here below. Okay, otherwise I equal to E, otherwise inside there, so you know, you can draw it towards the normal first, then away from the normal happens, actual ray can go this way. So these both lines should be looking parallel in your drawing, and you can see that a lateral displacement happens because actually light can go through this way, but due to the presence of glass slab it will laterally displaced little bit below, and that is called lateral displacement. Now students, this lateral displacement is very important, and dependence of the factor which influence this lateral displacement I will explain. First, you know, if angle of incidence is greater, if more angle of incidence will be there, lateral displacement will increase. Okay, if more angle of incidence will be there, like this way, suppose this will be the angle of incidence, then light can actually go this way. Here also more bending, more emergence will be there, so it will go upstairs similarly. So you know, angle of incidence more means lateral, LD means lateral displacement more. Refractive index more means lateral displacement more, because students, why? Because if the refractive index of glass is more, suppose another slab is there which is more refractive index, means more bending. More refractive index means speed of light on that medium will be very less. Less means it will be more bent towards the normal. Okay, you know that when light rays slow up, it will bend towards the normal, and if light ray will be fast, it will move away from the normal. So if more refractive index, more bending will be there, that means more lateral displacement. Similarly, if thickness more, students, thickness more means light ray move more distance. Okay, it becomes slower and lateral displacement. Similarly, students, there it has written in your book, you know, for violet color has maximum lateral displacement because of lambda minimum. Means if the wavelength decrease, lateral displacement will increase. Okay, if the wavelength of any light is decreased, its lateral displacement increase. That's why violet, remember this thing, question will come. Okay, so violet color has maximum lateral displacement and red is minimum, because red's lambda is maximum, that's why red has minimum lateral displacement, whereas violet has maximum lateral displacement. Students, remember this thing, if wavelength decrease, its mu means refractive index will increase. Okay, that's why lateral displacement also increase. Okay, so you can say that in violet, refractive index also higher. Okay, for violet color, refractive index higher means the speed of light, okay, in violet is least. Okay, so speed of light, oppositely you can say lambda increase, refractive index decrease. Lambda increase for red, so in red speed of light is less. Okay, speed of light is least. Students, sorry, one for mention, I forget to mention that red light speed is maximum. Okay, so I am showing you the book page, it will better if you read there. Okay, as you know, I am reading also here. Okay, the color or wavelength of light, the speed of light of all the colors is same, okay, in air, but in any other transparent medium the speed of light is different for different color. Okay, here you can see in a given medium the speed of red light is maximum, that of violet. Okay, therefore the refractive index of that medium is maximum, for violet it is least. Okay, here you can see for violet refractive wavelength less, that's why refractive index, here you can see I already told. Okay, and least for red light. Okay, so you know mu v greater than mu r, so mu v is higher. Lambda less for violet, that's why violet's refractive index is more. Okay, so this is the thing, students. I think you understand. Next lecture I will explain the second portion of the light.